quantum computing for the past 2 years. Ever since I joined college, it's been a field which was always interesting to me. And the especially qubits, there was no such club as qubits in my first year, but the seniors have been helping me since my first year. They've been helping me grow, and I too now want to give back to that community and give back to qubits. So I'll be holding an introductory session on qubits and um, the properties of qubits, and just a feel of what quantum computing is, so that we can delve into it, right, for a beginner. That's about me. Before I start, does anyone want to share their experience of quantum computing? Has anyone been interested in quantum computing? That's fine. If you're not comfortable, we can. By the way, you guys can switch on your cams and mics if you want. I'm not a professor, but okay, fine, cool, whatever, dude. I'll just present my screen then. Just a second. Is my screen visible?
Yes.
Okay, great. So let's get started then. Yeah, so why exactly are we getting into this? What is quantum computing, right? Why are we not satisfied with the computers which we have right now? Why are we not satisfied with supercomputers and computers which have unimaginable computing power? Well, let's start let's go to the most fundamental unit of a computer. What is it? It's a bit. And a bit basically has can take two values, right? It can take a 0 or a 1, right? We follow the binary system for that. And the problem with that is we are restricted only to those two values, right? And we now when we build chips, we can only fit a limited number of those bits on our chip. And we are at a stage right now where we are entering the phase of limitation to how many bits we can fit in a chip. Now, to tackle this problem, I'm pretty sure you guys are all familiar with this problem. And to tackle this problem, there have been countless innovative solutions to it. But let me tell you something, an upcoming technology which is completely going to revolutionize uh, computing forever, and that is quantum computing. So the fundamental unit of a quantum computer is a qubit. It's analogous to a bit, you can say. And a qubit can basically have a superposition of values. Now, I'm just going to be throwing terms here, so bear with me for now. So it's a superposition or a linear combination of zeros and ones. Okay, values of zeros and one. And basically, this 0 and 1, that is the ket of 0 and the ket of 1, are the orthogonal Z basis states or the computational basis. Okay, what is all this jargon? Okay, fine. Let's break it down further. I said a bit is a fundamental unit and it can take only two values. But what if we had a fundamental unit which can take infinite values, right? Or rather, it can be in a state of superposition of both 0 and 1. When we measure it, of course, it will collapse to either 0 or 1. But if we are able to manipulate the state of that qubit, imagine the amount of computational power which we'll have. just maybe, like around 30 qubits itself would give us a processing power of over a billion lines of code can be processed parallelly in um, with just 30 qubits. And that is the power of quantum computers. Where did I get that number? It's basically a formula where you just raise 2 to the power of how many qubits you have. And it's magical. So that is literally why this field exists and why we should be more interested in this. Okay, so that's a little bit about the qubit. But what exactly did I just say? What was I talking about ket 0 and ket 1? And like what does orthogonal z basis state mean? What are orthonormal bases? Yeah, let's get into that, because that, if we don't get the fundamentals straight, then we'll never be able to progress in this field, right? So I know you guys came here thinking that this is just going to be like a very small and like introductory session. It's a 1 hour session, so I'm going to fit how much ever I can in it. But there is going to be a bit of math, and like it may get a little bit complicated. Also, I am not a professor, so I may make some mistakes, and I really hope that yeah, because those mistakes will be completely, you know, uh, you guys can like unmute and like correct me wherever. So don't worry about that. So I'll just get into the details about how we proceed. So now we want to cover these following topics for now. These topics will get you familiar with the fundamentals of how to deal with qubits, and like just give you a grasp on like um, what is going to come in the future, and like how you can handle um, problems with the properties of these qubits, right? And so we have complex numbers, which is a must. Then vectors and vector spaces is going to be your M2, if you guys know what M2 is. I think first years here haven't done M2 yet, but it's going to be very basic, don't worry.
We are doing it right now. So
Cool, great then, no problem. So then there's matrices, and we'll go to the different kind of products which we can take, and of course normalization. So let's get on to it. So, what do you guys think a complex number is? You know, like you all know about the real numbers, right? And we know how real numbers are. But when someone talks about an imaginary number, we think it's not real, in the sense that we think that we have nothing to do with an imaginary number. There is no point in that, in the existence of imaginary numbers. But that's a completely wrong mindset to have. Complex numbers are very important to us, and they basically they are two parameters and they span a plane, and this plane is known as the Argand plane. And a real number set is a subset of the complex number, right? And simply, like if we set y is equal to 0 on the Argand plane, then we get back a real number line, right? So we know that much, I think. And then let's go on to vector spaces. This is just going to be like a quick refresher, okay? So like don't worry too much. Vector space is basically, um, they are a set, like a set V, which have two definite operators. That's the plus and the dot operator. Then they are called vector addition and scalar multiplication. So they all UVW, which belong to the set V, and CD, which belong to the complex plane. If they um, follow these properties, like if they satisfy these properties, then we can say that they span the vector space, right? UVW span the vector space. So I think these properties. Do you guys want me to go through them? I think they're pretty basic, and I think all of you should know this already.
Yeah, we
Uh,
know them.
yeah, pretty much. So let's just go on with the more juicy stuff. Yeah, so a vector, when I say juicy stuff, I come to vectors. You'll be like, what are you talking about? But trust me, vectors are really important. And a vector is basically a mathematical quantity which has magnitude and direction, right? And in Dirac notation, and this is where the new thing comes, right? So in Dirac notation, it's represented as ket of V. Now, it's interesting to note the unique name ket given to this symbol here with an arrow and like a V inside. So why exactly do we represent a vector in this ket? It's I'll come back to the naming little later on, but just consider that anywhere you see this ket of the vector v, that basically represents a vector in direct notation, right? So yeah, exactly. So right. So why exactly do we name it as ket? So the thing is, um, scientists love giving weird names. And there is a direct notation which follows the bracket notation. Okay, and it's all about um how vectors can be written. So in ket vector, basically it is a column vector consisting of two complex elements, which is given as so. And a bra vector is the um, complex conjugate of the ket vector, and it's written exactly symmetrically opposite, right? And together, if you look at it together, it'll form like a kind of bracket. And yeah, so scientists just named it bracket notation. I know it's very lazy of them. Anyway, so yes, matrix time. So I guess you guys know this basic stuff. I'm just putting it here so that like people who don't know matrices can just like familiar with it. So yeah, it's just a nice way to store numbers, and these operations we have defined on these quantities are very important in quantum mechanics, because matrices are how we represent qubits, right? And if we want to do operations on these qubits, or like manipulate these qubits, then we are going to have to talk about their operation on the matrix itself, right? And that is why matrix operations are so important. Anyway, so now we go to the transpose. Transpose, I'm sure you guys know, is basically, you know, this. So I'm pretty sure I don't have to go through all this, but like just take a look at what this does, right? A conjugate transpose is basically taking the conjugate of the transpose of the matrix. So it's like you can take the conjugate of the elements in the matrix and then take the transpose of that matrix, right? So cool. Now, if I take the conjugate transpose of a ket vector, I said I will get a bra vector, right? And what this means? So what this means is that um, we we have defined a vector space which ket vectors span into. And if you take the transpose of these vectors, if these vectors in the vector space, then we will get another unique vector, right? And this bra vector is these bra vectors span into another vector space, which is the complex transpose of the conjugate transpose of the ket vectors. So you can see in the bottom, the bracket of V is equal to the inner product. So let's see what does inner product mean. So if we take the element 2 minus 3i and multiply it with 2 plus 3i, plus if we take the element minus 5i and multiply with plus 5i, then we get the sum of that will give you 38. You can verify this for yourself. So basically, the inner product multiplies the element of the matrix with its complex with its conjugate transpose of the element itself. So the so is to to show the complex part of sorry, to show the conjugate of an element, we just put a star in the superfix of um, of the element, and so a star a is basically 2 minus 3i into 2 plus 3i, and b star b is minus 5i into 5, right? So yeah, now we go to the inverse of a matrix. I'm sure you guys should know what an inverse is, and I don't need to dwell on this much. This is a nice note. Matrices with det A is equal to 0 don't have an inverse, so we can keep that in mind. Yeah, and eigenvalues and eigenvectors. I'm sure you guys have done it in your M2 course. I'll just skim through this since already halfway through. So let's go on to the outer product. So we learned the inner product, right? The inner product is basically the where's this pen? Yeah. You guys able to see my arrow? That's fine. Never mind. Yeah. So basically, the inner product was like you multiply this element with this element, and then you add this element with this element, right? Now, if we come to the outer product, so the inner product was just a single. It gave us a single. Um, this times this, and this would give us a single element as the answer, right? So I'm sure you guys know multiplication rules, right, for matrices. So just like that, if we take the outer product would be the column vector times the row vector, and that would give us a matrix, not a single element but a matrix. And this is basically the formula for the outer product. These are just matrices till now. You can see that this is basically a column vector, this is basically a row vector, and just to refresh you guys, this column vector is basically represented a representation of a vector. Yeah, so and this brow of B is basically nothing but the super hard to write, right? The dagger of the ket of B. You know what's a dagger, right? Conjugate transpose, right? Complex conjugate transpose. And this is what you guys learned till now. If you guys have any doubts, just unmute and talk. And I'll keep going on. Okay, so so there were, till now we learned two products, right? One was the inner product and one was the outer product. Now this is the tensor product or the Kronecker product. Why is this special? Okay, so the first one gave us an element. Cool. Yeah, I don't know how to draw. Anyway, first one gave us an element. Second one gave us a matrix. Later on, you'll see that this is an operator. But yeah, okay, let's not get into that yet. And this third one, it's a tensor product of two matrices. Notice that the shape of these matrices are not the same, right? And so basically, the tensor product is given by this formula. One second. Yeah, the tensor product is given by this formula, where the element A naught is multiplied by the whole It is like B is multiplied by the whole A naught element, and the second row has A1 times B, right, as you can see. And now when we completely expand it, so what this is the shape of the matrix is going to take, right? So what you can see here is you can trace this back, right? So you can see that the tensor product here is actually a separable product. It's hard to trace back these, right? Given if we have an inner product 38, right? It's hard to trace back the initial conditions, right? If we have uh, if we have this matrix, it's hard to trace back A and B, right? But given this matrix, this is a separable matrix, and we can trace back the tensor product of A and B from this matrix. So that is a nice feature which we will take, which will be used later on. Right. So now we'll talk about the normalization of vector. Right. So if there is a vector, right. So if there is a vector x here, then the norm of x, we want it to be equal to 1. Okay. Why is that? Because we want vectors to be orthonormal in nature, right? Because then we can we can have a vector which has a property of being a unit vector as well as orthogonal vectors in a because orthogonal vectors in will span the vector space. They're the basis vectors and they span the vector space. So I guess you guys should know all this because you've done your M2. But like to normalize a vector, what we do is we divide the vector by its norm. Okay, and that's how you normalize a vector. And the inner product of a vector of a normalized vector will produce 1 as the answer. Yeah, okay. So now we covered the basic mathematics part. I guess this was nothing because like this is all things which you have done. You'll be so surprised, right? Quantum computing sounds so like weird, like quantum it has, and we're doing matrices and like vectors and like complex numbers and like why is this so easy, right? But then like that is the beauty of quantum computing. You already have the tools for all of this. Now it's time to explore with those tools and find mathematical models and find the beautiful reasoning of physics behind all this, right? So let's delve
Can
into.
you show the
Yeah, sure.
last slide?
Sure.
What is that quantity in the denominator on the left?
Norm. Okay. Yeah. I was getting to it later, but like basically this is just the root of the inner product of x, right? So okay, so this is what a norm is.
Okay, got it.
Fine. Okay, cool. Okay, so now next we'll jump to the nice bits. Eigenvalue. I'm sure you guys know what an eigenvalue is, right? So here's the definition. I'll just read it out geometrically. An eigenvector corresponds to a real non-zero eigenvalue, points to a direction in which it is stretched by the transformation, and the eigenvalue is the factor by which it is stretched. Okay. A visual example is given here, so you can just look into after transformation. You can see the change in the eigenvector. So yes. Okay, so now unitary matrix. I guess this is a term I'm not sure if you guys have done it, but okay, let's get into this. So a square matrix which where the conjugate transpose is equal to its inverse. This thing. Okay, so like this is a dagger operator. Okay, if you guys don't haven't followed it yet. So this is a dagger operator, and this basically indicates the conjugate transpose. Like for example, if this is the get of A, then the dagger of that is equal to the bra of A, right? We discussed this. So if the dagger of U is equal to the inverse of U, in other words, if you multiply U on both sides, right, then you'll get the identity, if you can see, right? U into U inverse is equal to I, that we know. And so that means U dagger is equal to U dagger, U is equal to I. And if you take the inner product of U, then you should be getting the identity matrix, right? You can like, because of this rule here. So U dagger, like, so this is U, right? And this is nothing but this. It's hard. Yeah, and if you multiply these two, then you're just going to get the identity matrix, right? Okay, so I think you guys got this. Hermitian. Okay, this is another very important matrix. And basically, the conjugate transpose is equal to the matrix itself, where U dagger is equal to U. And it's a very interesting property, which you will find pretty intriguing later on when gates and stuff comes up. So given a vector U, it's the bra of V is equal to the ket of V. So yeah, pretty much self-explanatory. Okay, now we'll go to superposition. Right. So I have been speaking about the, like qubit, and like, how it takes how it is a superposition of the states 0 and 1. So what exactly does superposition mean? So a fundamental property of quantum mechanics is that, when two or more quantum states can be added together, then the result is another valid quantum state. Okay, and that means that any quantum state can be represented as a sum of two or more other distinct quantum states, right? Distinct, that means they can't overlap each other. And any qubit state can be represented as a linear combination or a superposition of the two basis vectors, ket of 0 and ket of 1. So basis vectors, what are the basis vectors? Basis vectors are basically orthonormal vectors to each other, right? And they are the basis vectors can span the entire vector space. So you cannot represent the vector 0 in terms of 1 unless the coefficient of 1, like say this. One second. It's very hard to write. Yeah. Okay. So you cannot represent anything like this unless A itself is 0. Until A is not until A is 0, this is not valid. Okay. So those are basis vectors, and they can span the entire vector space. We say an arbitrary qubit state can be represented as a linear combination of these vectors, these basis vectors. Now let's get into what exactly is 0 and 1. So this is the 0 vector, which is a 1-0 column matrix, and this is the 1 vector, which is the 0-1 column matrix. Right, and Yeah, sorry, this is, I don't know how this came. But yeah, okay, so alpha beta is some arbitrary vector, let's call it state, arbitrary qubit state psi. Okay, and this state is represented as alpha times 0 plus beta times 1. Right? So that's the linear combination of the basis states 0 and 1. So if we talk about what exactly alpha and beta are, so alpha and beta can be any number. And now this is where the concept of complex numbers come into play. So alpha and beta can take even imaginary forms, and we consider them alpha and beta to be imaginary numbers. And this is because of this property of alpha and beta taking any value, we can represent the state psi in a sphere of sorts. Okay, and to get into that, we give it a name. It's known as the Bloch sphere. And alpha and beta, as you can verify here, alpha is cos theta and beta is e to the power of I phi sine theta, right? So so if you take the modulus of the square of alpha plus the modulus of the square of beta, it should sum up to 1. Okay, and because the states are orthonormal in nature, then the state psi is also orthonormal in nature, and that means it has a fixed amplitude, right? So that means it will lie only on the surface of the Bloch sphere, right? Does that make sense till now, whatever I said?
Can you say the last sentence again?
Yeah, so the state psi is its amplitude is fixed such that it can stay only on the surface of the Bloch sphere, right? The value is only somewhere on the surface of the Bloch sphere. So sorry, not value, the state. And yeah, so if I multiply the state psi with some kind of global phase e to the power of I don't know, I x whatever. So if I multiply it with this global phase, it will not affect the state psi. Okay, because global phases don't matter; they can just be discarded. The x in this case, so basically we have fixed ranges for theta and psi, as theta and phi. As you can see, theta can only range from 0 to pi, right? This thing here. So theta can only range from 0 to pi, and phi can range from 0 to 2 pi, right? You can see that. And with just this much, these many variables, we can construct any state psi on this Bloch sphere. Does that make sense? Okay. So now let's go on to another weird property, which is not that weird if you understand it. It's called entanglement. You guys must have heard Einstein say spooky action at a distance, right? For this. And this is where the general, the consensus is that quantum mechanics is like quantum computing, quantum mechanics is weird. So quantum entanglement, what is it? So it's a close connection between a pair or a group of quantum systems, right? So when two or more of such quantum systems come close to each other and interact with each other, they become entangled. Now, when two systems are entangled, if one of the systems changes its state, or if we change its state, right? Then immediately the change of state in the other system is triggered, and this this happens irrespective of how much distance you put between the two systems, right? So to sum it up, two systems, if they interact, they become entangled, and when you separate them and cause change in one system, the other one changes irrespective of how much distance they have separated. And if you happen to observe and determine the state of one of these systems, then fundamentally you will already know the state of the other system without having to measure or observe it. Okay, so guys probably should have a lot of questions in this side. Anyone has questions here till now? What I just said? No? Oh, damn! Everyone's smart. Okay, so let's put a hold on that entanglement and go to the next basis states. So I've already explained this. Can just have a. I'll just read this out. So it's fine. So while working in any space, we define some reference states to work in them. So for example, in the Argand plane, we use one I, or on Earth we use like latitude and longitude. Similarly, for quantum states, depending upon the size of the space, we have basis for these states. So for any n-dimensional space, we need an n linearly independent vectors set. Okay, and for the sake of simplicity, we choose orthogonal vectors. And in fact, especially in quantum computing, we work with orthonormal basis, and that means that vectors have unit magnitude. Okay, so these are just the concepts of the properties of qubits and what they are. And now let's get hands on. Let's do some quantum computing. Okay, let me just share my tab 1 second. Okay, I'm gonna share a link to whoever wants to do this. Just let me know if it's working.
Says binder not found.
Okay, fine. So I'll give you this link. Okay, go to this GitHub link. Then yeah. So after that, in learning path, go to the qubit tutorial. Do you guys get where I am?
Yes.
Okay, and over there, click on the here button. You can run the tutorial online here. So Quantum Katas is a repo in Microsoft, and basically they have this amazing tutorial in for quantum computing beginners especially. And I suggest you guys should do it. So for now, we'll just see the qubit tutorial, and we'll look at the code, and we'll look at the concepts. We'll have a little refresher, and then we'll look at the code also. I have about 15 minutes, so get it done. Yeah, so basically, like I said, they're explaining the concept of qubit, and how in classical computer a bit is either in a state of 0 or in a state of 1. But in qubit, it's the basic building block of a quantum computer, and it can be in a state of a 0 or in a state of 1, but it is not limited to those states, right? So it can be a combination or a superposition of these states. Yeah, so this is a very nice by the way, I'm going through this tutorial with you guys, along with you guys, so don't hold me to any mistakes or anything. But yeah, so a common misconception about quantum computing is that a qubit is always in a state of one or the other. We just don't know which one until we measure it. This is not the case. A qubit is a superposition is in a state between 0 and 1. When a qubit is measured, it is forced entirely into one state or the other state. In other words, measuring it actually changes its state. I'd like to think of it as, when we measure it, the state psi is now we are now interfering with that state psi, and because of that, we are creating a completely new state, and that is basically collapsing to either to one of the two basis states. Okay, so that's a nice way to think about it as well.
So a qubit has to be between 0 and 1, right?
So a qubit does not have a value until it's measured. Okay, so it actually, there is no meaning of saying a qubit has a value until it is measured. Okay, so what does that mean? That means that the state of the qubit is in a superposition state of 0 and 1, right? But it does not hold any value until after we measure it. After we measure it, we get back values. We get values depending on the probability of getting that value, right? So that is fine. But before we measure it, we can't say a qubit has a value. It's a superposition state. It's a state which is clearly defined, and we can't say that it has a certain value like 0 or like 1. Okay, so that's the point. Is that fine? Okay, moving on. Matrix representation. So the state of a qubit is represented by a complex vector of size 2. I don't have to. You guys have seen this already. And look at this point. A vector is normalized. That means the alpha square plus beta square is equal to 1, right? And alpha and beta are known as probability amplitudes of the state of 0 and 1, right? Okay, so let's move on to basis states. So a qubit in state 0 would be represented by the following vector 1, 0, and state 1 would be represented by 0, 1. And alpha, a random state psi qubit is a linear combination of these two basis states, alpha times 1, 0 plus beta times 0, 1. I think you guys got that clear till now. Now let's talk about the inner product of the basis states. So I remember what an inner product is. An inner product was the bracket of that state, right? So you can see the bra of 0 and times the ket of 0. So that is the inner product of 0 state, and we can see that is equal to 1. Similarly, the bra of 0, 0, 1 and the ket of 0, 1, that means the bracket of 1, that is also equal to 1. So the inner products, as you guys know how to take the inner products, right? So a star plus b star. So a star, since they are real numbers, so a star is equal to a. So 1 into 1 plus 0 into 0, which is equal to 1. Same here, 0 into 0 plus 1 into 1 is equal to 1. Now that means that they are orthonormal to each other. They are not orthonormal, they are the same basis vectors. But what if we took two orthonormal basis vectors? So that means we know 0 and 1 are orthonormal because we can't represent one with the other state, right? So if we take the inner product of the two, we should be expecting a value of 0, right? Do we get that? 1 times 0 is 0 plus 0 times 1 is 0. So yeah, so the inner product of two orthonormal basis vectors is always 0 unless the vector is itself, right? Any questions? Okay. So yeah, so we'll talk about computational basis. So computational basis, also known as Z basis, is very useful for quantum computing, and that is basically 1 0 and 0 1. So that is considered as a up state and down state. Okay, but there are other bases as well, and they have their own upstate and downstates. In fact, there are infinite amount of uh, kinds of orthonormal bases, right? And this just depends like on which one you consider your measurement in which basis. That is what it all boils down to. And there is an example here, the Hadamard base. This is pretty important. You'll, if you come to tomorrow's session also, you'll learn about this, especially in the gates part. I'll just skip this for now. So the Dirac notation, again here, we've gone through this quite a number of times, and how the arbitrary state psi can be represented as alpha times 0 plus beta times 1. We have other states as well, which is the plus state. This is the up state of the x basis, and it can be represented in terms of z basis as 1 by root 2 times 0 plus 1. Minus state is the following, and I and minus I is the basis vectors of the y basis state. No, y basis. So if you measure in y basis, you'll get a plus I or a minus I as the value in the end after measurement. So that can be represented in the computational basis as 1 by root 2 times 0 plus I times 1, and minus I is written here as follows. And so now we'll get into quantum computing, and it's how exactly, like what exactly is quantum computing? How do you do it? Okay, so yeah, we have like about 10 minutes, so it's not much to go. Right, so qubits are basically like, you know, a kind of data type for this library. The q hash is basically a package by Microsoft, right? And it's, you can code it in Python. On a physical computer, on a physical quantum computer, it's impossible to access the state of a qubit, right? You can't read its exact state. You can't you know, peek into its state and, like, you know, see what it is. You any you know, poking or pondering you do on that state is going to change the state itself, right? But in a, you know, q hash code or a quantum simulator, what you can do is you have diagnostic functions which can basically help you peek into the state, because it's a simulation. So you can do such things. It's very useful for like just learning or, like, you know, solving any errors in the programs. So that is why we need such libraries. And qubits aren't ordinary data types, so the variables of this type have to be declared and initialized a little differently. So they have given a initialization of the variable q, and they've assigned it to qubit function. Okay, and yeah, so use q is equal to qubit, right? So an alternative syntax could be use q is equal to qubit and open parenthesis. So basically your qubit is valid only in this block. So after that, it's no longer allocated outside the use block. Cool. Okay, so that is how to you know, how to code for how to initialize a qubit. Now we look at the different states of qubits, right? How do we change, how do we manipulate the states of that qubit which we just initialized? So as a thumb rule, whenever you initialize a qubit, you will be getting an initialized qubit or to the 0 computational basis state. Okay, so that means the up state of the z basis. That is your what do you call it? By default, that state is being initialized, and to basically change the state of the qubit, we have different functions which are available in the library itself. And now to represent, so let's directly go into the demo code, and examine the state of Q hash. So state of the qubit. So if you all want to just run this code, and then you're not connected, reload. Yeah, sometimes that happens. If you are idle for too long, then just loses connection. Give me a second. I guess whoever's following, if they ran the code, they would have got a particular table with the probability amplitudes and the state of the qubit in different um, states, right? Abhinav is asking, is it somehow related to Heisenberg's uncertainty principle? So Heisenberg's uncertainty principle, that is related to how the that is not related to any of the basis states. So I'm not really sure what the question was targeted to, but we're not using Heisenberg's uncertainty principle anywhere. Okay, has something's wrong from my end. Has anyone run the code till now? No response. Yeah, Paritosh, do you want to share your screen? I can help you out. Okay, now press Control and Enter. Okay, now go to Simulate Qubit demo, which is right below. Click on that, and now press Control and Enter. Cool. Scroll down a bit. Yeah. Okay. So this table, has everyone got it? Let me just present my screen. It's fine. Paritosh, just scroll up. Something's wrong from my end anyway. So, okay. So if you scroll all the way to the top of the code, there, yeah. So here, basically, what they're doing is they're representing the qubits in different states. Okay. So how do we get different states? First of all, what did I say? A qubit would always be initialized in its up state of the computational basis, right? So the starting q would be in its zeroth state, which is pointing up in the block sphere. Okay, so now when you put a C naught gate on it, so what is a C naught gate? That x of q is going to basically change the up state to a down state. Okay, and basically you will be having a state of 1 now. So as you can see, they have given state 1 as 100% probability. If you scroll down, then when you apply x of q, you'll get 100% probability of state 1. Okay. Now if you want state of minus was what? 1 by root 2 times 0 minus 1. Okay, that is the down state of the x basis, right? Now if you want that, then you basically have to apply Hadamard gate to the one state, and I'm not going to get into it, but that is another operation which allows you to rotate the qubit state in such a way that it lands up in the minus state on the Bloch sphere. Okay, and when it lands up in the minus state of the Bloch sphere, then the probabilities are equally distributed between the two states, two computational states, 0 and 1. Okay, you can observe all this in the output table. Just like that, yeah, since you've already come here. So yeah, so state minus has equal probability of state minus has equal probability of being 0th state and 1 state. Okay, and state minus I also has equal probability of being 0 state and 1 state, but you can see that there's a phase difference between the 1 state, and between minus and minus I, you can see that the phase difference is pi by 2. Can you guys see it? Can you see that arrow next to in the one column? Yeah, one row. Can you see that arrow is pointing differently? That gives a phase difference, and the phase difference only comes with the e to the power of I5 factor. Okay, does that make sense? And if you scroll up to the code once, the end part of the code, yeah, here the last few lines, it says Rx and Ry. So what that means is they are rotating the qubit with respect to x-axis by a certain angle 2 radians, and they're rotating the qubit with respect to the y-axis by a certain angle 1 radian. Does that make sense? And because of that, you're getting some uneven superposition of state of q, right? The q is now pointing some weird way in the Bloch sphere, right? And because of that, you have uneven distribution of probability amplitudes of the computational basis states. I was asking, like as you said, if we try to determine the state of the qubit, it changes the state of the qubit. As per Heisenberg's, if we measure the position, then the electron momentum gets changed and vice versa. And as far as I can remember, some implementations of the quantum computing use spin of electrons for qubits. I might be okay. So you're not wrong, but like quantum computing uses the spin of electrons for qubits. You're right over there. And yes, like I said, all these points are correct. So like I said, to determine the state, we will change the state itself, right? So if we try to measure the state or determine the state, we are in risk of changing the state itself. But that has nothing to do with Heisenberg's principle per se, because like Heisenberg's principle is completely different concept. Like, of course, that is one of the fundamental properties of quantum mechanics, and it is obviously tied into quantum computing. But the reason why I said that we changed by measuring the state collapses into one or the other is because we are affecting the state because we ourselves as observers have our own state, correct? We are our own state, our own quantum state. And now when we are trying to observe quantum state, then what we are doing is we are creating a tensor product between the quantum states, and we are changing the complete system, right? We are ourselves are changing the system of the quantum state, and it's becoming a new state itself. So that is why by measuring we change the state, right? So I hope that is clear. And do you guys have any questions regarding this code? I'm pretty sure you guys do have a lot of questions. Like, I mean, what is C0 gate, Hadamard gate, all that. If you guys come to tomorrow's session, you'll be able to learn that stuff as well. And you can literally, after tomorrow, I think you can make your own quantum programs and run it as simulations in your own devices. It's that easy. So I hope you guys enjoyed this session today. Have any questions? Anything to ask? Anything you felt I said wrong? Something is not sitting well with you?
Can you explain entanglement again?
Entanglement. Okay. So let me just. Yeah, okay. So basically, entanglement is like one of the most important quantum mechanical phenomena. The reason why it's so important is because like quantum computers, they rely on the fact that microscopic particles such as ions and photons, which can be represented as qubits, are mutually connected even if they are physically apart. So on a chip, right, you'll have like different qubits, right? And to like, we can make use of this entanglement property, and we can get information of different like, my point is like, they are all mutually connected even though they are separated by certain distances. And because of this phenomenon, we can create a quantum state containing two particles or two or more, but like two particles where the first particle, if it's like, say spin down, then we can 100% with 100% probability say the other particle is spin down or like spin up, depending on the correlation or anti-correlation or partial correlation as well. And so if you know the spin state of the first entangled particle, then we can make bold predictions of the second the spin state of the second particle as well. And this even though the probability of measuring up or down state for the first particle was some amount of probability, let us say 50% probability, but because of this correlation, we can say that the second particle is 100% whatever we predict. Okay. And that is why entanglement is so important, right? And this means that if we measure one of the two entangled particles, we can find the information of the second particle. It's as simple as that, and it's not really as simple as that at all. But like for now, this basic information is what you need to know. And I guess apart from that, yeah, one more important thing is it's a very delicate state. So an entangled state is a very delicate state, and the thing is, you can de-entangle the state very very easily. Okay, so simple, due to thermal radiation, simple vibration can de-entangle, decohere the two particles, and they will escape from being in an entangled state. And this is why they have to be isolated and like cooled down to such low temperatures. Plus like you need to be very careful when you're handling the entangled state of particles, because they can easily get affected by the surrounding environment. Their state can be affected by the state of the environment around it. So does that answer your question? Cool. So yeah, I think I took 10 extra minutes, but like, I hope you guys like the session. Yeah, so any other questions? Otherwise we can wrap it up. Cool then. I'll see you guys later, and do come for tomorrow's session as well. Ayushi, do you have anything else to say?
No, thanks, Pranav. It was a great session.
Cool, awesome. Okay. Thanks guys. Thanks for having me. Okay, bye bye.